Hi, I'm Thomas. Welcome to math class. This is lesson 3 on logarithms. Today we'll be covering logarithmic equations and graphing logarithmic functions. One scenario for which logarithms are particularly helpful is when we have variables in exponents. For example, the equation 9 equals 5 times 3 to the power of x. In order to solve for that variable, we're going to use logarithms. Now we can take the logarithm of both sides of an equation as long as both sides of the equation are positive. If our equation read 9 equals negative 5 times 3 to the power of x, then we wouldn't be able to use this technique. So this is when both sides of the equation are positive. I'm going to take the logarithm, and I could use the logarithm base 10, which is what I'll use, or the natural log, log base e, or a log of any base. For simplicity's sake, I'll simply use log base 10. So log 9 equals log of 5 times 3 to the power of x. And using my log laws, I'm going to, on the right side of the equation, show that this is equal to log 5 plus log 3 to the power of x. Continuing to simplify, on the right side of the equation, log 5 plus x times log 3. And I have, continuing on the left side of the equation, log 9. Now I will subtract the log of 5 from both sides. Log 9 minus log 5 equals x times log 3. I'll divide both sides by log 3. And now my solution is log 9 minus log 5 over log 3 equals x. And I can use my calculator to solve, and I get a value of approximately 0.535. 0.535 approximates x. When using logarithms to solve equations, it's important to check your solutions. It's always a good idea when solving algebraic equations to check your solutions, but particularly so involving logarithms, because some solutions will end up being not solutions. In this case, the way we would check the equation is to go to our original equation, 9 equals 5 times 3 to the power of x, and in the calculator calculate 3 to the power of 0.535, multiply that value by 5, and confirm that you get a value very close to 9, which in fact you do. Let's look at an example in which we end up with more than one possible solution, and when we check the solutions we find that they don't both work. This time we'll work through an example using the natural log. So we'll start with the equation natural log of x plus the natural log of x plus 2 equals the natural log of 24. Now we don't have exponents. We don't have variables in an exponent place. We already have an equation in terms of logs, the natural log. So let's apply our log laws to work through and find a solution for x, possibly more than one solution. And whatever solutions we do find, we're going to test them in the original equation. On the left side of the equation, I'm adding two terms that are of the natural log. They both are of a log to the same base, so I can combine as natural log of x times x plus 2 equals natural log of 24. Now that both sides of the equation are set to the same log, or the log of the same base, I can eliminate. Just like when I'm working with exponents, once I have an equation, both sides of the equation are at the same base, I can eliminate the bases and work with just the exponents. Now that I have both sides of the equation to the same log, using the same base of the log, I can eliminate, and now I'm left with x times x plus 2 equals 24. On the left side of the equation, I expand x squared plus 2x equals 24. I will subtract 24 from both sides to create a quadratic equation. X squared plus 2x minus 24 equals 0. I'll factor into two terms, which I can do using manual factoring. 24, two factors of 24 are 6 and 4, which I'm identifying because the constant is minus 24. I know I want two factors that will subtract to 2. 6 and 4 do the job, and I want the larger value with the plus. So I will have x plus 6 and x minus 4. My solutions are x is negative 6 or 4. Now when I test these by plugging them back into my equation, let's begin with negative 6. When I plug 6 into the original equation, the natural log of negative 6 plus the natural log of negative 6 plus 2 equals the natural log of 24. Now I don't go any farther because I have in two instances the natural log, or any log for that matter, of a negative number. Obviously the natural log of negative 6, that's a negative 6, and the natural log of negative 6 plus 2 would be natural log of negative 4. Those aren't possibilities for consideration, so I will eliminate negative 6 as a possible answer. As an important note, don't automatically eliminate negative solutions to variables. In this case, I can't have any negative solution because of the very first term of the equation, natural log of x. But I might be dealing with an equation, and one of the terms is the natural log of x plus 8. So if I were to work through in that particular situation and arrive at a value for x of negative 5, I could plug negative 5 into the expression natural log of negative 5 plus 8, and I'd arrive at the natural log of 3. So in that case, a negative solution for a variable would be a possible legitimate, valid solution to the equation. So don't automatically eliminate negative values for variables. Once you've solved, be sure to test them. Let's now test the value of 4. The natural log of 4 plus the natural log of 4 plus 2 equals the natural log of 24, which I can use my log laws to simplify as the natural log of 4 times 4 plus 2, which is 6, equals the natural log of 24, and those are both true. Both sides of the equation are equal. The natural log of 4 times 6 is 24, so we're saying that the natural log of 24 is the natural log of 24. Yes, that is true. So my solution, my one solution, is x equals 4. And this is what it looks like to prove, to validate, or verify the solution. Once you work through so that both sides of the equation are in fact true and you've eliminated your variable, that's a verification or a proof of your solution. Finally, let's work through an application exercise. I'll take an exercise from my textbook, which reads, the mass m of bacteria in a culture t hours after establishment is given by the equation m equals 25 times e to the power of 0.1 t grams. So I'm going to put that equation on the board. M equals 25 times e to the power of 0.1 t grams. Grams referring to the mass, the variable on the left side of the equation. So I'm going to manipulate the equation so that I solve for t. Now, until I have a value for m, I won't be able to solve for a value for t, but I will manipulate the equation so that it is set to the variable t. First thing I will do is I'll divide both sides of the equation by 25. And I have a note before I continue. What I observe is I have the variable t as part of an exponent. So I know I'm going to be using logarithms at some point. For now, I'm simply manipulating, working through my algebra to isolate t. So my first step is to divide both sides by 25. I now have m divided by 25 equals e to the power of 0.1t. Now I can use my relationships between exponents and logs to restructure the equation as follows. This is going to be the natural log. Actually, before I do that, let's trace and then do some simplification afterwards. I see that my base is e to the power of something. My base is e. So to set this up as a logarithmic equation, I'm going to start with log base e. Now I know I have an abbreviation, a simplified expression for log base e, so I'll eliminate log e and simply use the term natural log, which is using ln. That's the log base e. Now the value of this equation, the value of my original equation, I've manipulated it to be m over 25. And this is my value in my logarithmic equation. So the natural log of m over 25 is 0.1t. So this equation tells me that using natural logs to arrive at a value of m over 25, I apply the exponent 0.1t. Now I can do one more simplification. I can multiply both sides by 10. On the right, my 0.1 goes away, and now I have the equation 10 times the natural log of m over 25 equals t. And I can use this equation, given a particular mass, to identify the time required to reach that mass. So the question in my textbook is calculate the time required to reach a mass of 50 grams. 50 is my input for the value m, and I'll solve for time, which is t. So for m equals 50, I have 10 times the natural log of 50 over 25 equals t, which is 10 times the natural log of 50 divided by 25 is 2 equals t. And this is an exact solution. 10 times the natural log of 2 equals t. If I want to have a more meaningful solution, then I'll input these values into my calculator, input and calculate what is 10 times the natural log of 2. And using my calculator, I arrive at an approximate value of 6.93 hours. 6.93 hours approximates t. So it'll take just under 7 hours, given the equation, to reach a mass of 50 grams. Let's end this lesson here. I'll create a fourth lesson for logarithms relating to graphing. Be sure to practice these concepts with examples from your textbook, and I look forward to seeing you to work through graphing logarithmic functions.